Force of 90 Newton is applied to push this block up the ramp of length 10 meters. Length is given to you, it's 10, the force applied is 90 newtons, and the platform is 4 meters above the ground. Okay, it's 4 meters above the ground, and the weight of the box is 200 newtons right over here. Which of these could be used to determine the efficiency of the ramp? What's the formula for efficiency? Two formulas. Yeah.
Output over input.
Yes. Very good. So it's actually the useful output upon input. And the output and input, they can either be energies or they can be powers. Okay, so the output divided by the input. The total input, the total work which is put into moving the block up the inclined plane can be calculated if we simply multiply this force by this distance that it has traveled. So work done, the total work which is done on this block is force into displacement, right? This is the basic formula for work. So it's going to be 90 into 10. And now, what is this work being converted into? So they told us that it is being pushed up a ramp of length 10 meters and it is 4 meters above the ground and the weight of the block is 200 newtons. Okay, so this is actually our input. This is our total input. So we got our denominator over here, 90 into 10. So just from this fact that it's 90 into 10, I think this should be the correct answer. And yes, it should be C. See,
Yeah, it is C.
it's only C that has the 90 into 10 as its denominator and none of the others. Clear? Shortcut.
Yeah.
Okay, next. Now they're saying that a ball is dropped, it bounces once again and is then caught. Which of the following graphs of the gravitational potential energy against time could be used to represent the motion of the ball? Okay, this example of a ball being dropped is very frequently asked, especially in almost all the kinematics questions. Okay, so now again we have the ball, it is dropped, it hits the ground, it goes up and is caught. Now as it goes down, its height is decreasing, right? And as the height decreases, the gravitational potential energy, which you know is equal to mgh, as the height decreases, the gravitational potential energy should fall. So it's going to be a
Okay.
falling curve or a falling graph. So it's either A or C. It cannot be B, nor can it be D. Now, will it fall uh, in a curved fashion, or will it fall constantly? So well, for that you'll need to see to it what's happening to this. First of all, okay, we can't do that. Okay, what is the gravitational potential energy being converted into? It is being converted into the kinetic energy of the ball, right? As we go down the as the ball goes down, it is the potential energy gets converted into the kinetic energy of the ball, and the ball speed increases as it goes down. And just before hitting the ground, all of the potential energy has been converted into kinetic energy of that particular ball, right?
Right.
Okay, now the value for the formula for kinetic energy is half mv squared, and this velocity, as you know, is not constant. It is also increasing, right? As we go down the group, it is increasing according to equations of motion, because acceleration is present. So now if the velocity is increasing, it is not constant. This means that the rate at which the potential energy is being converted to kinetic energy is also increasing. It is not constant. Okay, it is becoming faster and faster. The potential energy is being converted to kinetic energy at a faster rate as time passes, because the velocity, it increases at a faster rate. So it's not going to be C, because C shows a constant fall in gravitational potential energy with time. It is going to be A. Is it A?
Uh, yeah, it's A.
It's A, yeah. So let me repeat this if you didn't get it. Over here, it's half mv squared. Velocity is increasing, therefore the kinetic energy has to increase. And kinetic energy is increasing because that potential energy was converted to kinetic energy. Now, this velocity is increasing not at a constant rate, but rather, okay, the velocity itself is increasing at a constant rate. But what about v squared? It's going to increase at an even faster rate. Or you could think of it this way. The kinetic energy is increasing. Okay, let me frame it again. As we go down, the velocity is changing. The kinetic velocity is not constant, it's increasing. So the kinetic energy has to increase. So potential energy gets converted to kinetic energy. And as we go down, it gets converted at a faster rate. And so it hits the ground. And then as it rebounds, it comes up. And the ball falls, hits the ground. It's just before hitting the ground, its velocity reaches a maximum value. It has a
Yeah.
certain height, which is s. Okay, let's assume the height is s. We need to see what's the relationship between this s and the potential energy. We actually need a relationship between the potential energy and the time. So for that, we'll need to see what's the relationship of the displacement and the time. Potential energy's formula is mgh, or in this case, mgs. Instead of h, I'm writing s because h and s are the same thing, right? Over here.
Yeah.
Now, this s, if I apply the equation of motion, s is equal to ut plus half at squared, this s is actually equal, because the u is 0, is equal to half at squared. The half and a are constant. So the s is proportional to the square of the time, correct?
Yeah.
From this equation, the potential energy is proportional to the s, right? From this, the potential energy is proportional to s
Okay. Yeah.
because the mass and the g are constant. And s
Mm-hmm.
itself is proportional to the square of t. We divide it from here, right?
Yeah.
So I can say that potential
So
energy is
okay,
proportional to the
it's
square of the
proportion
time.
to P.
So if it is proportional to the square of the time, whenever you have a square relationship, it's always a curve. If you remember this from your math, what was the graph of y against x squared? It's a curve, okay?
Okay. I got it now.
You got it now, got it. Great. So I'm glad I could explain this question to you. So basically it has this sort of logic behind it. So since it's proportional, it's, if this was direct relationship, then this would have been correct. But since it's a square relationship, it's going to be a curve, because as time doubles, the potential energy, it increases 4 times. So it's going to be a curve actually. Okay. So now, great. So next question then.
13 part C. Wait, 12 part C.
12 part C. Okay, this is your 12. All right, so again, a kinematics question. A student carries out an experiment to determine a value for g, the acceleration of free fall. A short wooden rod is released above a light gate. This is your light gate. This is a rod. It is released. Released means its initial velocity is 0. Then the timer is connected to this light gate. So as this rod crosses this light gate, it would have certain velocity with which it is crossing it. And then it falls down. A timer is connected to measure the time of the wooden rod to pass through the light gate. The experimental arrangement is shown over here. The student uses this equation and u is equal to 0 in the graphical method to determine a value for g. State the additional measurements that the student should take. So of course these are going to be time and um, time. You have the final, okay, the time is actually taken. He'll need to calculate to measure out this distance to which it has fallen. It's v squared equals u squared plus 2as. So it's just the distance that he needs, because u squared is already there, which is 0. V squared doesn't actually need it, but it can be calculated. Um, Actually, he doesn't need the v squared for it. Okay, G needs to be calculated, so the V squared also needs to be calculated beforehand. So in order to calculate the V is equals to U plus AT can be applied. So the time is already measured. Okay, so he doesn't need to measure anything else other than the distance he has traveled. What else was written in the marking scheme over here?
Let me check. Length of the wooden rod and distance from rod to light gate.
All right, this we did the distance from rod to light gate, but the length of the wooden rod, yes, that also needs to be measured because as it goes down, it could go down from, it could, the time is going to be measured when the rod is going to be, its base is going to be over here. So this distance has to be deducted from the total distance to measure the distance that it has traveled. So, okay, yeah. So these are the two distances that he needs to measure. Then describe how the velocity as it passes through the rod through the light gate can be determined accurately. Okay, so velocity can be determined accurately. Okay, accurately, they've given this term over here, and you need this, describe how the student can determine a value for G using the graphical method. Okay, so basically for this, V squared equals U squared plus 2AS needs to be applied, which will give you the value for acceleration. But for determining the velocity V, we don't need this equation at all because we don't have the acceleration. So we are going to use the formula that lacks acceleration. It's S is equals to U plus V upon 2 into T, because we don't have the acceleration, right? We don't have this over here. We
Yeah.
need to determine this in the next step. So we can use this formula. And the distance, what's going to be the distance? The distance is actually going to be the total distance minus the length of the rod. Okay, the length of the rod minus the total distance through which it fell, because that's
Okay.
actually the distance which it has traveled. Okay, so the distance traveled is going to be the distance from the rod to this light gate minus the length of the rod. Distance to rod minus the length of the rod. Length of rod, distance from the rod to the light gate. The rod to light gate. Once you have the distance, you plug it in here, get the value for V by placing U as 0 and the time which has been measured. You can also do you can take more than one readings for measuring the time accurately. Uh, take take two or take 5 to 6 readings. Take at least five readings for the time and take their average. 5 readings for time and calculate the average for accuracy. Calculate average for accurate time measurement. Okay, is this what the marking scheme said, or is it something different?
Is that V is equals to length of rod divided by time
V is
to
equals
pass
to
through the gate? Length of rod divided by
length of rod divided by time and
time to pass through the light gate, which is written in brackets. And then the second point is repeat at each height and calculate an average.
they didn't mention the two. Okay, so over here, length of rod divided by time that passes through the gate, which will give you the, no, how is this possible? This isn't correct. Wait, let me see.
This doesn't make sense, right?
Yeah, wait, just a second. Because the rod is falling down, it's a free fall motion, so it will be accelerating. This isn't the formula we can apply over here. This is not a uniform motion, unless they have told us they carried out acceleration of free fall needs to be determined as it passes through this place. So V is the final velocity before hitting this light rod, light gate. So we can apply V is equals to, no. S is equals to V plus U upon 2 multiplied by the time. So it's going to be 2S divided by V plus U divided by, actually not V plus U. Wait, I'll tell you what they've written. Okay. So they've used the same formula but in a different way. S is equals to V plus U upon 2 multiplied by time. This U is 0, so it becomes V upon 2 multiplied by time into S. And so the time actually equals, no, sorry, not time. The velocity equals 2S upon time, right? 2S divided by time is equal to the velocity. Now, this is what the velocity actually is. The 2S is the length. 2S is not the length of the rod, and the time passes through the gate. Length of rod, distance from the rod, repeat at each height and calculate an average. Okay, they've used an experimental approach over here that we repeat at each height and then calculate an average for the height. Oh, sorry, for the this velocity. Length of the rod, if you have the length of, so basically this wooden rod,
Also, like if we use like the formula V is equals to ST, no, not that
S is
one.
equals to VT.
S is equals to VT.
Yes, yes, we can apply that. This is actually that formula, and this is when we assume that this speed is constant, and since the distance over here is very small, this distance is just the length of this rod, so we are assuming that it is roughly constant as it passes through this point.
Right.
That's why we can apply that formula to calculate the velocity, okay, instead of doing this, because we don't have the time for this rod to fall from here to the light gate. Okay, it didn't tell us anything about the timer being started when it is dropped. It told us that the timer is just connected to the light gate, so it will only start when this rod, it hits the light gate or it passes through the light gate. Okay, it starts and stops when it enters the light gate, and as soon as it leaves it, the timer stops, and so it measures the time it takes to pass through the light gate. So we can apply the formula instead of this formula, because we don't have the time. We can erase this out. We could apply the formula as velocity is equal to length of the rod divided by time can be used to calculate the velocity. And for accuracy, we can take many lengths, sorry, not length, you can take many measurements and then take their means. Many measurements from different heights. Okay, many measurements from, wait, not from different heights, from the same height actually, but different repeated measurements from the same height. What did they say? Repeat at each height and calculate an average. Okay, so height has basically, the height needs to stay constant for the speed to stay constant at that particular time, at that particular point over here. If you want the same speed to be measured over here, this height should be the same. It shouldn't change. Okay, so many measurements for each height means that from the same height actually, and then take the mean. They're saying each height means actually when you'll take it again to that particular point, so you won't be able to place it accurately exactly at this point, right? It's going to be slightly above or below, so you're just going to take a bit like average point over here, somewhere over here. So that's why they said from each height. So you many measurements taken from each height, and then you take out the average, and you get the accurate velocity and take out average.
Okay.
Okay, and this is, we are assuming that velocity at this point where while it is passing through the light gate is constant. Okay, then describe how the student can determine a value for G using the graphical method. Okay, so using the graphical method, how can we determine the value for G using the formula V squared equals U squared plus 2AS? The U is is zero. Wait, is it zero? Is the U zero? Yes, it is zero because it's dropped from there,
Yeah.
from here. Okay, and this entire length has also been measured in the beginning. that length is actually this displacement over here, this one. U is 0, so it becomes 2as equals v squared. Now we need to find out an acceleration of free fall, meaning find out the value for g. So just make a the subject, it's going to become v squared upon 2s, right? So basically, all right, instead of making a the subject, just focus on this equation over here. It's an equation of v squared equals 2as. The 2 and the a are constant. So we can draw out an expression or an equation of v squared being proportional to s. Right? We can develop this relationship. V squared is proportional to s, to the distance from which it is thrown
Yeah.
or from which it is dropped. So we can take different values of v. We can calculate different values of v, and from while dropping it from different heights. Okay, so that's the reason why they said for each height. Okay, now you should get it. Over here they said for each height, right? From each height. They actually meant from each height. They actually meant that when you take out different values of v. So take many measurements from every height that you, from every new height that you take, and then calculate the average of those measurements only. For
Yeah, right.
instance, over here, if let's say our value for s is 1 meter, and the value for v turns out to be, let's say, 10 meters per second, what you do is you do this, you did the same experiment which was described above. You take this rod again at 1 meter's height, and then you try calculating a second value for v, and let's say now it turns out to be 9.8 meters per second, and then you again do the same thing and you calculate another value for v, which turns out to be, let's say, 10.1 meters per second. And all those values from that particular height, when you calculate their average, that will give you an accurate value for v for that height. So what you're going to do is, in the graph, you're going to plot a graph of v squared against s. Okay, you're going to plot a graph of v squared against s. Okay, where s is going to be the height, the distance from which it is dropped, and v is going to be the final velocity. And that graph is going to be calculated. Whatever the graph shape is, okay, over here, since these are directly related, so it's going to be a straight line passing through the origin. In that case, in that graph, if you look at this equation over here, what does the 2a represent? Does the 2a represent the slope?
Yeah.
It represents a slope, right? So this graph that you have plotted, you're going to calculate its gradient and equate that gradient to 2a, and then to calculate the value for a, you're going to divide the gradient by 2, and you'll have your value for g.
Okay.
Okay, so this is the basic method, the graphical method. So let's compare this with the marking scheme as well. Okay, they've given us some slide description over here. Okay, repeat at different heights above the light gate and calculate the value for v of each height. Okay, they've done the same. They've actually repeated this statement, that repeat different values of heights and then calculate the value for v for each height. Okay, we've done this part over here, that you take several values at different heights. Okay, that's the reason. That's how you're going to get your values on the x-axis, and for each corresponding height you get your values for the v, and then you square those v's, and then states an appropriate graph to draw. Okay, you can have different graphs. Okay, you can have v squared against s, you can have any of these combinations which are over here. And then the one which we drew was this one, v squared against s, right? V squared against s,
Yeah.
this one. So the gradient is going to be 2, gradient upon 2 is going to be equal to the acceleration, and so when you multiply that by 2, you'll get your the gradient has to be equated to the 2a, and then it will give you your acceleration. Okay, so this is a third statement, states an appropriate graph to draw. So that appropriate graph is this one over here, and corresponding description to how to obtain the acceleration from the gradient, it's that at this point. So we actually got all the points from here. Okay, v squared against s, we mentioned that, and how to calculate the gradient, we also mentioned that, and we also mentioned that we need to take different heights and their corresponding v values. Clear? Now is this part clear? But I hope you know how to write this in wording. Should I write it in
Yeah,
wording?
yes.
All you need to do is just write down this expression. Till here, it's fine, okay? After this, you mentioned that they repeat this for different heights and calculate their corresponding values of V,
Okay.
or measure their corresponding values of V, and then plot a graph of V squared against S, and you'll get a straight line passing through the origin, and then calculate the gradient of that line, and that gradient is going to equal the twice of acceleration, and then the acceleration is going to be half of the gradient. Okay, so this will
Okay.
give you all the points,
Okay.
right? Should I move on?
Also, sir, can we do like a unit 3 papers?
Yeah,
We
sure.
haven't done that at all.
Volume is
Yeah.
constant. The volume is not changing because the egg shell is what determines the volume. The shell is not breaking, right? The shell is not breaking because it's just
Yeah.
the gases that are leaving it. The rho is the density of the fluid in which the egg is immersed, and the density is again constant, and G again is constant. Upthrust is not changing, it's constant. W is reducing, the weight is reducing. So if the weight is reducing and upthrust is constant, then that actually means there is a resultant force developing upwards, and
Okay.
therefore it will start accelerating upward, because acceleration's direction is always the same as that of the resultant force. Clear?
Yeah.
So that's all you need to write. Clear?
Yeah.
Okay, next. Um, did you do this? Momentum. Oh, we did cover this. We did? Did we cover
Yeah, we
momentum?
did.
We did. Okay.
Yeah.
Did you attempt the paper, this question?
No.
Okay, great. So this is a scale diagram that you need to draw, and it's pretty basic. You can do it yourself, okay? If if you find problem, you can send it to me. And
Yeah.
principle of conservation of linear momentum, that's theory. Initial velocity, again, you're going to use m1 u1 plus m2 u2 equals m1 v1 plus m2 v.
Yeah.
But over here, you'll actually need to split them into components, okay? Because this is now a two-dimensional motion, vertical and horizontal. So if you remember that lecture in which we did the two-dimensional motion, I did compare those. Okay, so and then over here we have a European Space Agency sent this probe to Mars. As the probe approaches the surface of Mars with a vertical velocity component of 460 meters per second. Again, this seems like a question from kinematics again. So you can use this question easily. Once the vertical velocity of the probe has reduced to 75 meters per second, a parachute was removed and the thrusters were switched on. Due to error in the thrusters, was switched off too soon, leaving the probe to free fall to the surface of the Mars, impact with the surface, and then it crashes. Then the parachute was used as was used over a decrease in height of 9.7 kilometers, show that the average vertical deceleration of the probe to shoot the parachute was about 11 meters per second. Okay, so you can do this easily. You've got the height is given to you, the deceleration is asked, although its value is given to you, the initial velocity is gonna be given to you as well. It's given to you, it's for a 60 meters per second, and you need the acceleration, and that's it. They've given you the height, they've given you the initial velocity, they want to calculate the acceleration, so, and they've even given you these intervals over here. So what do you think? What formula should I apply over here? Let's apply the formula. Okay, we don't have time, so we cannot apply that. We do have the final velocity. The final velocity over the parachute was used over a distance of 9.7 kilometers. So the parachute, when it was removed, the final velocity was 75 meters per second. Initial velocity is given to you. The height is 9.7 kilometers. So what formula can I use when time is not given? V squared equals u squared plus 2as, right?
Yeah.
Height is given, initial and final are given, acceleration is needed. You can
Okay.
use this and calculate it. Okay. Then the next stage says that the parachute was at an angle of to the vertical. Okay, this is the vertical, and it is at an angle of 6 degrees to the vertical. Actually, sorry, this is the vertical, and this is the angle of the parachute to the vertical. Now, the total resistive force acting on the parachute and the probe was at an average of 6 degrees to the vertical. Calculate the magnitude of the average total resistive forces. You may neglect the mass of the parachute. Now, the mass of the probe is given to you. The gravitational field strength of Mars is also given to you. All you need to do is just calculate the magnitude of the total resistive forces that act on this probe. Now, the total resistive forces acting on the probe at an average of an angle 6 degrees. Okay, you've got the weight, which is 600 kg when you multiply it with 3.8, 3.8 Newton per grams, because newtons per kg, because on Mars the value for gravitational field strength is 3.8. They've given it to you over here, right? So G is 3.8 on Mars. So when you multiply them, you'll get the weight of this probe. And once you have the weight of
Okay.
the probe, this weight of the probe acts downwards. And where will the resistive forces be acting? The resistive forces are mainly going to be acting in this direction, right? At an angle of 6 degrees to the horizontal. Now, if they're acting at an angle of 6 degrees to the horizontal, let me tell you one thing. This actually is a triangle. If you look at it carefully, this is a triangle that we have made, which is a right angle triangle with an angle of 6 degrees over here. Now, over here in this case, the vertical weight acts downwards, right, opposite to this part of the triangle, right, to this component of this vertical forces. The resistive forces are acting in this direction. They told us it's acting at an angle of 6 degrees, 6 degrees to the vertical. These are the resistive forces. The vertical component of the resistive forces is balancing the weight, right? It's balancing the weight. So this actually means that the weight and the vertical component are exactly the same, right? So instead of writing down the vertical component, I can write 600 multiplied by 3.8. Now I have this, I have the 6 degrees over here, I have the R. Can I use any trigonometric ratio to calculate the value for R? Which one should I use, sine or cos?
For the R,
Yes.
um, cost.
Okay, so please calculate it.
Okay.
Make sure your calculator is in the degree mode. And I hope you know how to switch between degree and radians as well.
2292.6.
Yep, that's the answer. 2.3 raised to the power of 3, or 2.29 raised to the power of
So
3.
wait, what did you mean by the radian mode?
There is a different mode as well in the calculator, radiant. But you don't need to do it if you don't even need to know it if you don't have
Wait,
math.
sir, your voice.
Radian mode. There's a different
Okay.
mode of calculation. Which pressure is this? 16. A part 2. Part 2. It's 8690. We got a different answer. This in minus f cos of theta equals 100 times minus 10.6. 10.6. We have the acceleration from the previous part as well. We didn't calculate the acceleration from here. We'll need the acceleration of free fall. Okay, let's redo this question then. We'll need the first part
Voice
answer.
decreased again.
We'll need the first part's answer for doing the second part. Now, in the first part, it says that the vertical deceleration of the probe due to the parachute was about 11 meters per second square. Show that this is the value. So, okay, can you okay, using this method, it's gonna be final velocity, which is 75 squared, equals initial velocity, which is 460 squared, plus 2 times It's 9.7 is kilometers, so multiplied by cube times acceleration. Get a value for A, please. 275 squared minus 460 squared divided by 2 times 9.7 times 10 cube. What's the answer to this? It's going to be negative.
Oh, yeah, minus 106172668.04.
Minus 10.6 meters per second squared. Not that. It's 75 squared minus 460 squared divided by 2 times 9.7 times 10 cube as well. Okay, I think you missed this out, or you missed out the
Oh wait,
squares.
I believe that says negative minus 3.
Oh, okay. Please change that.
Oh yeah, it's minus 10.6.
So minus 10.6 meters per second squared. This is the deceleration that is provided by the resistive forces of the parachute. Okay, this is a deceleration that has been provided. This means that the net force in that case was acting in that direction, in the direction opposite to the direction of velocity. That's why it's negative. Now see, in this part we actually did a little mistake over here. It's not this method. They didn't tell us anywhere that the parachute is falling at a constant velocity. Okay, if it was falling at a constant velocity, then the weight would have been balanced by the vertical component and there would have been no resultant force at all. But over here they told us that it is decelerating. Right, in the first part we calculated the magnitude of the deceleration as well. So now we are going to use that and find out the value for the resistive forces, magnitude of the average total resistive forces that are acting on this body. So now this diagram, as far as this diagram is concerned, this is the resistive forces, but how did we calculate the resistive forces? How can we do that? Well, we can do that by again making a triangle of forces. You've got this 6 degrees force acting in this direction as the resistive force. You've got the weight acting downwards, right? This component over here is actually the r cos of 6 degrees, right? This r
Yeah.
cos of 6 degrees, and this is the weight. And now since the parachute is it's decelerating, so the r cos of 6 degrees minus the weight is gonna equal the mass multiplied by the acceleration of this probe. Remember Newton's second law, which says the greater force minus the lesser force is equal to ma. Actually, F is equal to ma, this formula. F is the net force, right? The net force is gonna be, you're gonna not subtract that R from W, because R is not acting directly against W. It's the R cos of 6 that is acting against W, okay? And
Okay.
also it is decelerating. Decelerating means that the resistive forces are more than the weight itself. Okay, deceleration always means that the resistive forces are more than the weight or the forward force. So now the resistive forces, the bigger forces minus the smaller forces will give you the ma. The acceleration given to you is minus 10.6, but you are not going to place a negative sign here, okay? Because that already has been taken care of while we were making this equation. All we need now is just to calculate the magnitude of this R. So this is going to become R cos of 6 equals ma plus W, and R is equals to ma plus W divided by cos of 6 degrees. Now just plug in the values. The values for the mass is 600 kg. The values for the acceleration is 10.6, which we calculated in the previous answer. The value for the weight is the mass multiplied by its gravitational field strength, right? 3.8. W equals mg divided by cos of 6. And I hope this will give us the correct answer. Let me check it out. This certainly will give us the correct answer. Yep. There we see they place a negative sign here because they, if you look at this part, it's mg minus f cos of 6, right? So that's why they used a negative sign over here. Whereas for us, we used the ma minus mg, meaning the f cos of 6 or the r cos of 6 minus mg equals ma. So we don't need to use the negative sign over here. We use the r cos of 6, the greater force minus the lesser force equals ma. Then you don't need to change the sign of acceleration. It's always going to be positive. But in this case, they use the opposite side. They use the mg minus f cos of 6. That's why they had to place the negative sign here. Okay, or forget that point. It's just this statement, and this will give us the correct answer. If you calculate it, please calculate the answer to this.
Okay.
What is it? It's 8700 Newton, meaning 8687, approximately 8700 to 2 Newton, to two significant figures actually. You get this part? What did you not
No.
get? No? Okay. All right, that's great. Now you got it. Okay, so see, the probe was in free fall from a height of 3.7 kilometers, reaching the surface of Mars with a velocity of 150 meters per second. Explain whether the term free fall is correct in this context. Your answer should include a calculation. The gravitational field strength is given to you is 3.8 newtons per kg. Well, what motion do we call free fall when it is on Earth? When the acceleration is 9.81 and it's constant at that particular value, and the air resistance is negligible, and 9.81 is actually the gravitational field strength of Earth, right? In this case, if you look at it, the gravitational field strength of Mars and the height is 3.7 kilometers, right? The velocity is given
Yeah.
to you. All we need to do is just calculate the acceleration. If that acceleration turns out to be the same as the gravitational field strength of Mars, then yes, it's in free fall. And if no, then otherwise it's not. Get it? Because see, free fall
Yeah.
motion is the one in which if it is on Earth, the acceleration should be 9.81. But if it is on Mars, then the acceleration is going to be equal to the g of Mars. Okay, and the g of Mars given to us is 3.8 Newton per kg. So now all we need to do is just calculate the acceleration of this motion. So the height is given to us. The surface reaching velocity is given to us. The surface reaching velocity means the final velocity. The initial velocity is also given to us. The initial velocity is, if you look at the probe again, parachute was removed, thrusters switched on. Then as soon as the thrusters were switched off, its velocity was 68 meters per second. Its velocity was 68 meters per second. From here, it fell to 150 meters per second. And the height has been given to us. The height is, where is the height? Okay, it's in the next part. It's 3.7 kilometers. Okay, so height is 3.7 kilometers. The final velocity is 150 meters per second. The initial velocity is 68 meters per second. Try calculating the free fall acceleration before me. Come on, Farwa. So 3.7, and the time taken is it given? It's not given. Okay, no problem. We can use the formula that doesn't require time. V squared equals U squared plus 2AS, right? What's the formula? What's the value for V? It's 150 squared. The value for U is 68 squared. Acceleration needs to be calculated. The kilometers needs to be converted to meters. Okay, it's going to be 3.7 times 10 cube. Now calculate the value for acceleration. Is going to be 150 squared minus 68 squared divided by 2 times 3.7 times 10 cube, which is equal to the acceleration. And acceleration is, please calculate the answer. It's 150 squared.
2415675.
Okay,
2.4 to 10 to the power of 1, 2, 3, 4, 6.
it's 2.42. I think I'm getting 2.42. Please recheck what you plugged. It's 3. It's 10 cube. It's not -3. What's the marking scheme saying?
Yeah, I got 2.4.
Yep, it's 2.4, correct. Okay, meters per second squared. Now this 2.4 is different from the, it's not the same, right? The 2.4 is not the same as the gravitational field strength of Mars, right? So no, it's not free fall motion. Now let's see what are they saying. Accelerated acceleration of free fall is 3.8. So comparison of the calculated value. So not in free fall, and we got the full marks.
Yeah.
Okay, so this was an additional point that we needed to add, but yes, it's not under free fall because this acceleration that we calculated is not equal to the acceleration of free fall. Acceleration of free fall is 3.8 meters per second squared for Mars, because that's actually equal to the gravitational field strength of Mars. 17. Stress strain graph. Okay, this is again deformation. This should be easy. Okay, I would suggest you try this question on yourself, okay, because it looks pretty good question. Manufacturer leaves blocks to dry for at least 28 days before use. Discuss why. Okay. And then this is again an inclined plane question. Again, a video. It should be easy. We've covered all of this inclined plane stuff as well. Again, an inclined plane continuation of that, and then this completes the paper. So yeah, do one thing. Try completing the rest of it. Okay. Now we are gonna do unit 3.
Okay.
Yeah. Which of the following is not an SI base unit? Ampere is an SI base unit. Kelvin is an SI base unit. Second is a base unit, but watt is not a base unit. A diagram shows a vernier scale. Which of the following is the reading of the scale? Okay, for vernier scale, all you need to do is just, first of all, there are two scales. This is the main scale, and this is the vernier scale. Vernier scale. All you need to do is just measure see their measurements and then add them up. So for the main scale reading, you need to see the point just before the 0 mark of the vernier scale, okay? Just before the 0 mark, it's this line over here. This is the reading of the main scale. And in this case, it's 19, right? It's 19.
Yeah.
And for the vernier scale reading, the coinciding point is the reading. Okay, in this case, it's this one, not the others. Okay, it's just this one, because this line is coinciding with the other line. So it's 1, 2, 3, 4, 5, 6, 7. It's 7. So you're not gonna add 19 and 7, but rather you're gonna add 19 and 0.7. Okay, because the vernier scale reading is always divided by 10. So this is gonna become 19.7. Hopefully that's the answer. Let's see. Yep, let's see. Okay, they've given us 19.6 as a closer answer. Oh, wait, this is not 7. This is 6. This is 6. Sorry. This is 6. C is the correct answer. Okay. See, 1, 2, 3, 4, 5. Wait. Not even 6. It's 5. It's not C, it's B. 1, 0, 1, 2, 3, 4, 5, 6. Then 7, 8, 9, 10. Yeah, this is 6. C is the correct answer actually. Okay. Get it? 0.6 actually.
Also,
Now,
the 0 point, like,
yeah, the zero error.
yeah.
Yes. Question 345 refer to an experiment to determine the viscosity of a liquid. The definition of viscosity is the fluid friction. Okay. So now let's see. A student dropped a sphere into a measuring cylinder. Okay, this is the most common example of fluid dynamics. A sphere being dropped in oil or in liquid in a measuring cylinder. This is actually an experiment. Now, she measured the time taken for the sphere to fall through a given distance in the liquid and repeated this several times. She recorded the times as 2.4, 2.5, 1.9, and 2.5 seconds. Which of the following is the best statement for the time of the sphere of fall to fall? Okay, If you look at these statements, these times 2.4, 2.5, and 2.5 are very close to one another. In fact, these are the same values, but 1.9 is an outlier, right? It's an odd one out. So you're gonna leave it out and you're gonna take the average of the rest. Okay, that's the trick. Get it?